So now that we've established that the trig functions aren't actually invertible, let's see if we can define the inverse trig functions. Um, I I say this a little tongue-in-cheek, but at the same time, it's a real problem. Um, think about the function y equals x squared. Right? The squaring function. The graph looks like a parabola. Well, if that doesn't pass a horizontal line test, right? So that's not really invertible. And yet we think of square rooting as being the inverse of squaring all the time, right? We think of y equals the square root of x as being the inverse of x squared. But if you look at the graph of the square root function, it's not this graph tipped, reflected over the line y equals x. It's only half of this graph. That is, there's another half of this parabola that we ignore. When we talk about the square root function, we talk about the positive square root. So we've made a choice. We said, nah, this isn't really invertible, but we want a function that at least inverts some of it. So the thing is, what I'm doing is I'm saying I'm really only looking at half of this parabola. Put some blinders on. Don't look at the whole thing. Pay no attention to the man behind the curtain, right? Pay no attention to the left-hand side here. That this half of it alone does pass a horizontal line test, and so this half, when I flip it over, does pass a vertical line test. So no, this is not an invertible function, but if we just look at half of it, if we restrict it to being x bigger than 0, then we get this thing here where y is bigger than 0, right? That the restriction on x turns into a restriction on y. We don't want the negative square roots, we only want the positive square roots. We're going to do the same thing for our trig functions. So here we go. Let's start with y equals sine x. Okay. Y equals sine x, as you know very well, looks like this. Right? If I were to try to invert that, the graph would be a sine curve going up the y-axis. So let's see if we can draw that in red here. Right? It would be the sine curve going this way, up and down the y-axis. So this in blue is the graph of y equals sine x. This in red now is the graph of x equals sine y. Right? I don't want x equals sine y. I want y equals inverse sine of x. So, but this is not a function. It doesn't pass a vertical line test. There's just too many spots. So like up here, I have to say, well, what part am I going to look at? Okay, and essentially I'm going to look at the stuff that's as close to 0 as possible here. So let's pick green, and I'm saying if I look from this spot right here to that right there, that gives all of the range, or actually domain, I guess, from here to there exactly once. Once I get past here, it starts coming back down again. I'm getting y values up here for x values that I've already used, right? This comes back over. This gets all of my x values. The part of the graph that comes from the sine curve, is from the lowest spot here at -1 up to the highest spot there at +1, right? The x values here were from -π/2 to +π/2, right? So essentially what I'm doing here is I'm saying take the sine, y equals sine x, where x is between -π/2 and π/2. These are my blinders. As I'm saying, don't look at the whole graph, just look from here up to there, just that part. That gives me y values that are between -1 and 1. That's the complete possible outputs that the sine could give anywhere, right? So I'm getting everything, but I'm getting it only once, okay? And so then my inverse sine, define y equals sine inverse of x for the x values now between -1 and 1, and the y values between -π/2 and +π/2. The roles of x and y are reversed. Here x was between -π/2 and +π/2. Now I'm going to have y between minus pi over 2 and pi over 2. The x values are restricted. So originally the y values are restricted from minus 1 to 1. Now my x values are going to be restricted from minus 1 to 1. Okay. So y equals sine inverse of x if x equals the sine of y. Right? But not just any old x. X has to be between minus 1 and plus 1, and not just any old y. The output here will be somewhere between minus pi over 2 and plus pi over 2. All right? Just like with the square root function, we didn't say, yeah, there's two square roots, but when we say this function, we mean just the positive square root. When I say the angle whose sine is a half, there's a lot of angles whose sine are a half, but I only mean the small one. Sine inverse of a half, the angle whose sine is a half, is, in radians, pi over 6. Okay. Notice, minus pi over 2 to plus pi over 2. This is in quadrant 4 for my negative angles, or quadrant 1 for the positive ones there. Arc sine will only give you answers between minus pi over 2 and plus pi over 2, fourth quadrant or first quadrant, because that's the choice we make. We could have said, no, let's invert this part here, in which case we would have gone from pi to 2 pi and gotten second or third quadrant angles. But that's not the choice that was made. We decided to use this part of the sine curve and invert it. Okay. There's inverse sine. Let's take a look at inverse cosine. So, looking at the graph first of all, the cosine curve looks like this. Right? Again, doesn't pass the horizontal line test, so it's not really invertible. But I want to just put my blinders on and take a part of it that covers all my bases, but only does it once. Right? So if I look at this piece of the cosine curve here, from 0 to pi, it starts up at 1, goes down as low as minus 1, and it hits all those y values only once. Right? So right here I've got, let's see in blue, I've got y equals cosine x. The x values I'm going to restrict from 0 to pi. Notice that's first or second quadrant angles. And the y values, the outputs here are between minus 1 and 1. So when I invert it now, define y equals the angle whose cosine is x, or the inverse cosine x, or the arc cosine x, if x equals cosine y, where x now is between minus 1 and 1. The restriction on y now becomes the restriction on x, and y is somewhere between 0 and pi. The output of the inverse cosine is going to be somewhere between 0 and pi. That is, when I look at this graph and I invert it here, so let's do this in green, it ends up looking like, all right, it's a cosine curve that's headed up the y-axis. Gets all the way up here to pi. It goes as low as minus 1, goes as high as plus 1 on the x direction. Right? It's this part of the cosine curve reflected over the line y equals x. Okay. Remember, the output is an angle. So if on this one I said something like, what's the angle whose cosine is a half? What's the arc cosine of a half? What's the inverse cosine of a half? All of those mean the same thing. Then give me an angle whose cosine is a half. 1 over 2. That angle would be pi over 3. Right? That's a 60-degree angle there, pi over 3. If I said give me an angle whose cosine is negative a half would look like this. Minus 1 over 2. Could be there, or it could be down in the third quadrant, but we've made the choice that this is the angle we're talking about. So that's actually 2 pi over 3, 120 degrees, right? I want to do, what have we got in 10 minutes? I want to do the inverse tangent while we're here. So I've got y equals tangent x. Remember, tangent x is one with a bunch of vertical asymptotes here, so it goes through 0. It's got this vertical asymptote at pi over 2. Another one down here at minus pi over 2. Looks like this. Got the sound effect as it goes in there. And also backwards. Intercepts there at the pi's, right? At pi and at 2 pi and so on. Okay. Definitely not invertible. Does not pass the horizontal line test. So I got to put some blinders on. And what I do is I say, let's just look at the small angles. Let's pick just this piece of the tangent curve. Just that right there. Because that covers the whole output of the tangent all the way from minus infinity to plus infinity. And it does it only once, right? Each y value is only attained once. So that when I invert it now, it's going to look like this. Let's do this in green. Where the original one has vertical asymptotes, this one actually has horizontal asymptotes at pi over 2 and minus pi over 2. Alright, so let's write this down. How much time I got left? I only have 15 minutes per video, otherwise YouTube doesn't like it. So here we go. We're starting with y equals the tangent of x, right? X is being restricted between minus pi over 2 and plus pi over 2. The y value still goes from minus infinity to infinity. I guess you don't really equal infinity, you just get close. And so now I'm going to look at the inverse. Y equals the inverse tangent of x if x equals tangent y, but I've got restrictions, all right? The x value now could be anything you want from minus infinity to infinity. The rule of y now becomes the rule of x, and the y is restricted to being between minus pi over 2 and plus pi over 2. And I'm putting equal signs in here, but it never actually equals pi over 2 because of those asymptotes. All right, so those are all strictly less thans. Right? Inverse sine, inverse cosine, inverse tangent. Those are the three functions that your calculator uses. I'm going to have to define the other three as well, but I'm going to do that a little differently. But for now, there's the basic definitions. We'll work with these in future videos.